Imagine you're standing on Earth, looking up at the stars, and suddenly you witness something that shouldn't be possible. A burst of light from a distant galaxy appears to race across the cosmos faster than light itself should travel. Your mind races with questions. Have we been wrong about the fundamental laws of physics? Is Einstein's theory of relativity broken? Today, we're diving into one of the most mind-bending questions in all of physics. Is the speed of light really the fastest speed in the universe? Or have we discovered something that shatters this cosmic speed limit? If you're curious about these cosmic mysteries, make sure to subscribe to this channel and give a thumbs up. For over a century, physicists have told us that nothing can travel faster than light in a vacuum, approximately 299,792 kilometers per second. This isn't just a rule, it's supposedly the fundamental architecture of space-time itself. Yet astronomers keep discovering phenomena that seem to mock this cosmic speed limit. Galaxies racing away from us faster than light should allow. Quantum particles that appear to communicate instantaneously across vast distances. Jets of matter erupting from black holes that seem to exceed light speed. What's really going on here? To understand this cosmic mystery, we need to start with why light speed became the universal speed limit in the first place. In 1905, a young patent clerk named Albert Einstein published a paper that would revolutionize our understanding of the universe. His special theory of relativity didn't just suggest that light speed was fast. It revealed that the speed of light in a vacuum is the same for all observers, regardless of their motion. This seemingly simple idea has profound implications that ripple through every aspect of modern physics. Think about this for a moment. If you're in a car moving at 60 miles per hour and you throw a ball forward at 20 miles per hour, someone standing on the sidewalk sees the ball moving at 80 miles per hour. That's just common sense, right? But light doesn't work this way. Whether you're standing still or racing through space at half the speed of light, when you measure a beam of light, it always moves at exactly the same speed. This bizarre property isn't a quirk of light. It's a fundamental feature of how space and time themselves work. Einstein's equations revealed something even stranger. As objects approach the speed of light, time itself begins to slow down for them relative to stationary observers. Mass increases toward infinity. The energy required to accelerate further approaches infinite values. These aren't just theoretical predictions. We observe these effects every single day in particle accelerators around the world. At the Large Hadron Collider near Geneva, protons are accelerated to 99.999991% the speed of light. Despite the incredible energies involved, they never quite reach that ultimate cosmic speed limit. But here's where our story gets interesting. While Einstein's relativity sets this firm boundary, the universe seems to have found some fascinating loopholes. Let me tell you about the first one that had astronomers scratching their heads: quasars with superluminal jets. In the 1970s, radio astronomers using newly developed very long baseline interferometry techniques made a shocking discovery. They observed jets of material shooting out from quasars, incredibly bright galactic nuclei powered by supermassive black holes, and these jets appeared to be moving at several times the speed of light. The astronomical community was in uproar. Had they discovered something that violated the most fundamental law of modern physics? The mystery deepened as more observations poured in. The Very Large Array in New Mexico, the Arecibo Observatory in Puerto Rico, and radio telescopes worldwide confirmed these seemingly impossible measurements. Blobs of matter in these jets appeared to traverse distances in just a few years that light should take decades to cross. The faster-than-light motion wasn't a measurement error or an illusion. It was repeatedly observed and verified. The resolution to this paradox is both elegant and mind-bending. These jets aren't actually moving faster than light. Instead, they're moving at speeds very close to light speed, but at an angle almost directly toward us. This creates a projection effect that makes the motion appear superluminal. Imagine a jet moving at 95% light speed at a small angle to our line of sight. The light from the jet's starting position takes a certain time to reach us. But because the jet is moving almost toward us at nearly light speed, the light from its later positions doesn't have to travel as far. The time delay between seeing the start and end positions is compressed, making the jet appear to cross the sky faster than it actually moved through space. This explanation, confirmed by decades of observations and refined calculations, demonstrates something crucial about our universe. What appears to violate the cosmic speed limit often reveals deeper truths about the nature of space, time, and observation itself. The universe is full of illusions and perspective tricks that challenge our intuitions while ultimately confirming our fundamental theories. But superluminal jets were just the beginning. Let me tell you about something even stranger: quantum entanglement. In 1935, Einstein himself, along with colleagues Podolsky and Rosen, proposed a thought experiment that would haunt physics for decades. They imagined pairs of particles that remained mysteriously connected even when separated by vast distances. Measure one particle, and its partner instantly knows what state to be in, regardless of the distance between them. Einstein famously called this spooky action at a distance, and believed it showed that quantum mechanics must be incomplete. For decades, this remained a philosophical debate. Then, in the 1960s and 70s, physicist John Bell developed a way to test whether this instant connection was real or whether particles had predetermined states. The experiments, first performed by Alain Aspect in the early 1980s and refined many times since, delivered a shocking verdict: quantum entanglement is real. Particles can indeed be instantly correlated across any distance. This discovery sent shockwaves through the physics community. If information can be transmitted instantly between entangled particles, doesn't that violate the speed of light limit? Scientists at CERN, MIT, and research institutions worldwide have spent decades grappling with this apparent paradox. The answer, as it turns out, is both yes and no, and understanding why requires us to think very carefully about what we mean by information. When you measure an entangled particle and it randomly chooses a state, say spin up, its partner instantly becomes spin down, even if it's on the other side of the galaxy. The correlation is instantaneous. But here's the crucial point: you can't use this to send information faster than light. The measurement results are random. You can't control what state your particle will be in, so you can't encode a message. It's like having two magic coins that always land on opposite sides, but you can't control whether yours lands heads or tails. The universe seems to have built-in safeguards against faster-than-light communication, even while allowing instant quantum correlations. Recent experiments have pushed these tests to extraordinary scales. In 2017, Chinese scientists using the Mischius quantum satellite demonstrated entanglement between particles separated by over 1,200 kilometers. The correlations remained instantaneous, yet no usable information could travel faster than light. It's as if the universe maintains two different sets of rules, one for correlations and another for information transfer, and it carefully ensures that the cosmic speed limit remains unbroken for anything that could violate causality. But the universe had more surprises in store. Let me tell you about the discovery that made headlines worldwide. The expansion of space itself can exceed the speed of light. This isn't science fiction. It's happening right now, and it's been confirmed by observations from the Hubble Space Telescope, the Planck satellite, and ground-based observatories around the world. Here's what's happening. Space itself is expanding. Not just the galaxies moving apart through space, but the actual fabric of space-time is stretching. Imagine drawing dots on a balloon and then inflating it. The dots aren't moving across the balloon's surface, but they're getting farther apart because the surface itself is expanding. That's what's happening to our universe on the largest scales. The farther away a galaxy is from us, the faster space is expanding between us and that galaxy. There's a distance, called the Hubble radius, beyond which galaxies are receding from us faster than the speed of light. We can still see these galaxies because the light they emitted in the past reached us before they crossed this threshold, but the light they're emitting right now will never reach Earth. These galaxies have effectively disappeared beyond a cosmic horizon, racing away faster than light itself can travel. Speaking of cosmic extremes and mind-bending phenomena, if you're fascinated by these violations of our everyday physics, you might enjoy my video on the rarest objects in the universe. I explore things like magnetars with magnetic fields so strong they could disrupt your molecular structure from thousands of miles away, and hypothetical quark stars that shouldn't exist according to conventional physics. The link is in the description and pinned on the comments. The Sloan Digital Sky Survey has mapped millions of galaxies and confirmed this superluminal recession. Galaxies at distances of about 14 billion light-years are moving away from us at the speed of light. Beyond that distance, which we call the cosmic event horizon, galaxies are receding even faster. The observable universe has a radius of about 46 billion light-years, even though the universe is only 13.8 billion years old, precisely because of this faster-than-light expansion. This raises a mind-boggling question. If space can expand faster than light, could we somehow harness this for faster-than-light travel? This brings us to one of the most fascinating theoretical possibilities in physics, the Alcubierre warp drive. In 1994, physicist Miguel Alcubierre proposed a solution to Einstein's field equations that would allow faster-than-light travel without technically violating relativity. The concept is elegantly simple in principle, though impossibly complex in practice. Instead of moving through space faster than light, you would compress space in front of your spacecraft and expand it behind you. You'd be surfing on a wave of warped spacetime, remaining stationary relative to your local space while that bubble of space moves faster than light. It's not science fiction, it's a legitimate solution to Einstein's equations. NASA's EagleWorks laboratory has actually conducted preliminary research into warp drive concepts. Harold White and his team have explored whether the energy requirements could be reduced from impossible to merely extremely challenging. The original Alcubierre drive required energy equivalent to the mass of Jupiter. White's modifications might reduce this to the mass of a spacecraft, though even this remains far beyond our current technological capabilities. But wait, there's another cosmic phenomenon that seems to violate the light speed limit, the infamous tachyon. Tachyons are hypothetical particles that always travel faster than light. They emerge naturally from certain equations in physics, particularly in string theory, but they come with bizarre properties. As a tachyon loses energy, it speeds up. To slow down to the speed of light would require infinite energy. They would travel backward in time from some reference frames, potentially violating causality itself. Despite decades of searching, no experiment has ever detected a tachyon. Particle physics experiments at Fermilab, CERN, and other accelerator facilities have found no evidence for these faster-than-light particles. Most physicists now believe that tachyons, if they appear in a theory, indicate that the theory has a fundamental instability rather than predicting real particles. But the search continues because discovering a tachyon would revolutionize our understanding of the universe. Let me tell you about another phenomenon that initially seemed to break the light barrier: neutrinos. In 2011, the Opera experiment at Gran Sasso, Italy, made a stunning announcement. They had measured neutrinos traveling from CERN, 730 kilometers away, and the particles appeared to arrive 60 nanoseconds earlier than light would have. The news sent shockwaves through the physics community. Had we finally found particles that could exceed light speed? The scientific community responded with appropriate skepticism. Extraordinary claims require extraordinary evidence, and a measurement contradicting a century of relativity needed rigorous verification. Teams worldwide scrambled to check the results. The Minos experiment at Fermilab, the T2K experiment in Japan, and others attempted to replicate the findings. Meanwhile, theorists worked overtime trying to understand how neutrinos could possibly travel faster than light without breaking everything we know about physics. 6 months later, the mystery was solved, and it was both embarrassing and enlightening. The Opera team discovered 2 technical errors. A fiber optic cable carrying timing signals was improperly connected, and an oscillator used for timing had been running fast. When these errors were corrected, the neutrinos were traveling at exactly the speed they should, just below the speed of light. The episode wasn't a failure. It was science working exactly as it should. A surprising result was announced, scrutinized, tested, and ultimately corrected. This is how we build reliable knowledge about the universe. The neutrino story reminds us of something crucial. The speed of light limit has survived every experimental test for over a century. Every time we think we've found an exception, deeper investigation reveals that the universe is even more clever than we imagined in maintaining this fundamental boundary. But that doesn't mean nothing can appear to exceed light speed. Let me explain one of the most beautiful examples, Cherenkov radiation. If you've ever seen photographs of nuclear reactors glowing with an eerie blue light underwater, you've witnessed Cherenkov radiation. This phenomenon occurs when charged particles travel through a medium faster than light travels in that medium. Notice the careful wording, faster than light in that medium, not faster than light in a vacuum. Light slows down when passing through water, glass, or any other transparent material. In water, light travels at about 75% of its vacuum speed. But energetic particles from nuclear reactions can exceed this reduced speed, creating the photonic equivalent of a sonic boom. The Super Kamiokande detector in Japan, buried 1 kilometer underground, uses 50,000 tons of ultrapure water to detect neutrinos through their Cherenkov radiation. When a neutrino occasionally interacts with the water, it produces charged particles that race through the water faster than light can travel there, creating distinctive rings of blue light. The Cherenkov technique has detected neutrinos from the Sun, from cosmic ray collisions in Earth's atmosphere, and even from supernova 1987A in the Large Magellanic Cloud. This brings us to a fascinating category of apparent faster-than-light phenomena: group velocity versus phase velocity. In certain situations, the peak of a wave can travel faster than light, while the actual information carried by the wave cannot. It's like watching ocean waves where individual wave crests race forward and disappear, while the wave packet as a whole moves more slowly. Scientists have created laboratory conditions where the group velocity of light pulses exceeds c, the speed of light in vacuum, but no information or energy actually travels faster than light. Lijun Wang and colleagues at NEC Research Institute demonstrated this dramatically in 2000. They sent a light pulse through a specially prepared cesium vapor and observed the pulse peak emerging from the chamber before it had even finished entering. The peak had traveled at 310 times the speed of light. But before you start planning your faster-than-light communication system, here's the catch: no information actually traveled faster than light. The pulse was reshaped in such a way that it appeared to exit early, but you couldn't use this to send a signal faster than light speed. Now let's venture into the realm of cosmological mysteries that challenge our understanding of light speed. During the first fraction of a second after the Big Bang, the universe underwent a period called cosmic inflation. In just 10 to the negative 32 seconds, the universe expanded by a factor of at least 10 to the 26. Space itself expanded so rapidly that regions of the universe became causally disconnected. They moved apart faster than light could travel between them. The evidence for inflation comes from multiple sources. The Planck satellite has mapped the cosmic microwave background radiation with exquisite precision, revealing patterns that match inflation's predictions perfectly. The BICEP and Keck array experiments at the South Pole have searched for gravitational wave signatures from inflation. The uniformity of the cosmic microwave background temperature across regions that should never have been in causal contact provides compelling evidence that inflation really happened. Alan Guth, who proposed inflation theory in 1980, showed that this faster-than-light expansion solves several fundamental puzzles about our universe. Why is space so flat? Why is the cosmic microwave background so uniform? Why don't we see magnetic monopoles? Inflation answers all these questions, but it requires space to expand much faster than light speed during that brief explosive epoch. This brings us to wormholes, hypothetical tunnels through space-time that could connect distant regions of the universe. If wormholes exist, you could potentially travel between galaxies in moments without ever exceeding light speed locally. You wouldn't be moving through space faster than light. Instead, you'd be taking a shortcut through a higher dimension. It's like an ant walking along a folded piece of paper. It can step from one side to the other without traversing the entire surface. The mathematics of wormholes comes straight from Einstein's general relativity. The Einstein-Rosen bridge, proposed in 1935, was the first mathematical description of a wormhole. But these theoretical wormholes are unstable. They would collapse instantly, faster than light could traverse them. To keep a wormhole open, you'd need exotic matter with negative energy density, something that may not exist in sufficient quantities anywhere in the universe. Kip Thorne and his colleagues at Caltech have extensively studied traversable wormholes. For the movie Interstellar, Thorne calculated what a wormhole would actually look like if one existed. The visual effects team used his equations to create the most scientifically accurate depiction of a wormhole ever put on film. But despite their theoretical possibility, no astronomical observation has ever detected evidence of a wormhole. The Laser Interferometer Gravitational Wave Observatory, or LIGO, has opened a new window into testing these exotic possibilities. When LIGO detects gravitational waves from merging black holes, scientists can test whether the merger follows general relativity's predictions precisely. Any deviation might hint at exotic physics like wormholes or extra dimensions. So far, every observation has confirmed Einstein's theory to extraordinary precision. Speaking of gravitational waves, here's something remarkable. These ripples in space-time itself travel at exactly the speed of light. When LIGO detected the merger of two neutron stars in 2017, designated GW 170817, something extraordinary happened. Telescopes around the world also detected light from the same event. The gravitational waves and the light had traveled 130 million light-years and arrived within seconds of each other. This simultaneous arrival proved that gravity itself propagates at light speed, just as Einstein predicted a century ago. This observation killed dozens of alternative theories of gravity in a single stroke. Some theories had proposed that gravitational effects might propagate instantly or at some other speed. But nature has spoken. Gravity obeys the same cosmic speed limit as light. The Virgo detector in Italy and the two LIGO detectors in Washington and Louisiana have now confirmed this with multiple observations. Every merger, every gravitational wave event, reinforces this fundamental truth. But here's where quantum mechanics throws us another curveball: quantum tunneling. This phenomenon allows particles to seemingly teleport through barriers that classical physics says they shouldn't be able to cross. Imagine rolling a ball toward a hill. Classical physics says if the ball doesn't have enough energy to roll over the hill, it will roll back. But in quantum mechanics, the ball has a chance of suddenly appearing on the other side of the hill without ever going over it. Quantum tunneling isn't just theoretical, it's happening in your body right now. The sun shines because protons tunnel through the electromagnetic barrier that should keep them apart. Without quantum tunneling, nuclear fusion in stars would be impossible, and we wouldn't exist. Scanning tunneling microscopes use this effect to image individual atoms. Some transistors in your computer or phone rely on quantum tunneling to function. Here's the mind-bending part. Some experiments suggest that quantum tunneling might be instantaneous. The Hartmann effect, first predicted in 1962, suggests that the time a particle takes to tunnel through a barrier doesn't increase with the barrier's thickness beyond a certain point. Recent experiments at the University of Toronto and Griffith University in Australia have measured tunneling times in attoseconds. That's 10 to the negative 18 seconds. Some measurements suggest the tunneling time might actually be 0. Does this mean information can travel faster than light through quantum tunneling? The answer appears to be no. While individual tunneling events might be instantaneous, you can't control which particles will tunnel and when. The probabilistic nature of quantum mechanics once again preserves causality. The universe seems determined to prevent faster-than-light communication while still allowing these strange quantum phenomena. Let's shift our focus to dark energy, the mysterious force accelerating the universe's expansion. Discovered in 1998 through observations of distant supernovae by two independent teams, dark energy comprises about 68% of the universe's energy density. The Supernova Cosmology Project and the High-Z Supernova Search Team shared the 2011 Nobel Prize in Physics for this discovery that shocked the cosmological community. Dark energy's effects become more pronounced over time. As the universe expands and matter becomes more dilute, dark energy's influence grows stronger. Current models suggest that in the far future, hundreds of billions of years from now, the expansion will accelerate to the point where galaxy clusters, galaxies, solar systems, and eventually even atoms will be torn apart in what cosmologists call the Big Rip. Space would expand so rapidly that the observable universe would shrink to nothing, with every point racing away from every other point faster than light. The Dark Energy Survey, using the Blanco telescope in Chile, has mapped hundreds of millions of galaxies to understand this mysterious force better. The Euclid Space Telescope, launched by the European Space Agency in 2023, is conducting an even more comprehensive survey. These observations consistently show that dark energy is real, it's accelerating the expansion, and it's pushing distant galaxies away from us at ever-increasing speeds. Now let me tell you about virtual particles, quantum fluctuations that pop into existence and annihilate in times so brief they seem to violate the energy conservation law. The Heisenberg uncertainty principle allows energy to be borrowed from the vacuum for incredibly short periods. The more energy borrowed, the shorter the time before it must be paid back. These virtual particles are everywhere, filling what we call empty space with a seething quantum foam of activity. Virtual particles aren't just mathematical abstractions. They have measurable effects. The Casimir effect, where two metal plates in a vacuum are pushed together by the pressure of virtual particles, has been measured precisely. The Lamb shift in hydrogen atoms, a tiny change in energy levels caused by virtual particles, was one of the first confirmations of quantum electrodynamics. These particles appear and disappear faster than light could travel between them, yet they're fundamental to how our universe works. Here's something even stranger. According to quantum field theory, virtual particles can temporarily travel faster than light. A virtual photon, mediating the electromagnetic force between two charged particles, can for brief moments exceed light speed. This doesn't violate causality because virtual particles can't carry information. They exist only as intermediate states in quantum interactions. Once again, the universe has found a way to allow seemingly impossible phenomena while preserving the fundamental rule that information cannot travel faster than light. The Large Hadron Collider has pushed our understanding of these quantum effects to new extremes. When protons collide at 99.9999991% the speed of light, the energy density becomes so extreme that virtual particles become real. Einstein's famous equation, E equals mc squared, works in reverse. Energy converts into matter. These collisions briefly recreate conditions that existed microseconds after the Big Bang, when the entire universe was hot enough for such transformations to happen naturally. Let's talk about cosmic voids and the large-scale structure of the universe. Galaxy surveys have revealed that matter in the universe is arranged in a vast cosmic web, with galaxies forming filaments and walls surrounding enormous empty voids. The Sloan Great Wall, discovered in 2003, stretches over 1 billion light-years across. The Hercules Corona Borealis Great Wall, identified in 2013, spans 10 billion light-years, more than 1/10 the diameter of the observable universe. These structures are so vast that light takes billions of years to cross them. Yet they formed and evolved as coherent structures, which raises a profound question. How did different parts of these structures know how to evolve together when they're separated by distances that light couldn't traverse during the age of the universe? The answer lies partly in inflation, which allowed these regions to be in causal contact before being stretched apart, and partly in the fact that gravity's effects, while traveling at light speed, have been accumulating over cosmic time. The Boötes supervoid, discovered in 1981, is an enormous region of space containing very few galaxies. Spanning 330 million light-years in diameter, it's one of the largest known structures in the universe. Light takes over 300 million years to cross this cosmic desert, yet its very existence tells us something about the speed of information flow in the early universe. Such large underdense regions could only form if the initial conditions were set up when the universe was much smaller, before inflation pushed everything apart faster than light. Now consider this mind-bending possibility. What if the speed of light itself isn't constant? Some theoretical physicists have proposed that the speed of light might have been different in the early universe. João Maguejo and Andreas Albrecht suggested this variable speed of light theory as an alternative to inflation for solving cosmological puzzles. If light traveled faster in the early universe, it could explain the horizon problem, why regions of space that should never have been in causal contact have the same temperature. Testing whether fundamental constants like the speed of light have changed over cosmic time is extraordinarily difficult, but not impossible. Astronomers study the spectra of distant quasars, looking for subtle changes in the fine structure constant, which depends on the speed of light. The Very Large Telescope in Chile and the Keck telescopes in Hawaii have searched for such variations. So far, the results are consistent with the speed of light being constant over at least the past 12 billion years, though some controversial observations hint at tiny variations. Let me tell you about closed time-like curves, pathways through spacetime that loop back on themselves, potentially allowing travel into the past. General relativity, surprisingly, doesn't forbid time travel. Specific solutions to Einstein's equations, like the Gödel metric discovered in 1949, describe universes where time travel is possible. The Alcubierre drive, if it could be built, might allow not just faster-than-light travel, but also journeys into the past. The grandfather paradox, what happens if you travel back and prevent your own birth, has puzzled physicists for decades. Stephen Hawking proposed the chronology protection conjecture, suggesting that the laws of physics somehow prevent closed time-like curves from forming. Perhaps quantum effects destroy any would-be time machine before it can operate. The fact that we've never encountered time travelers from the future might be evidence that time travel remains forever impossible, no matter how advanced technology becomes. But there's another possibility that preserves both relativity and causality: the many-worlds interpretation of quantum mechanics. In this view, traveling to the past doesn't change your original timeline, but creates or shifts you into a parallel universe. The grandfather paradox dissolves because you're not killing your grandfather in your own past, but in an alternate timeline. While this sounds like science fiction, it's a serious proposal supported by some prominent physicists. Let's examine frame dragging, one of general relativity's most bizarre predictions. Massive rotating objects like Earth actually drag spacetime around with them, like honey being stirred by a spoon. NASA's Gravity Probe B mission, which operated from 2004 to 2005, confirmed this effect using incredibly precise gyroscopes orbiting Earth. Near rotating black holes, frame dragging becomes so extreme that space itself is pulled around faster than light relative to distant observers. Inside the ergosphere of a rotating black hole, the region where frame dragging becomes irresistible, space moves faster than light relative to the outside universe. Nothing can remain stationary in the ergosphere. Everything must rotate with the black hole. The Penrose process, proposed by Roger Penrose in 1969, shows how energy can be extracted from this region, essentially mining the rotational energy of the black hole. Some active galactic nuclei might be powered by this mechanism. The Event Horizon Telescope, which produced the first image of a black hole's shadow in 2019, is now studying rotating black holes to observe these effects directly. The supermassive black hole in Galaxy M87, whose image captivated the world, is rotating at a significant fraction of its maximum possible speed. Future observations might reveal the warping of spacetime around these cosmic monsters, showing us regions where the conventional laws of physics break down. Consider the quantum Zeno effect, where frequent observation of a quantum system can freeze its evolution. By measuring an unstable particle frequently enough, you can prevent it from decaying. This has been demonstrated experimentally with trapped ions and other quantum systems. Some interpretations suggest that information about the quantum state is somehow transmitted instantly throughout the system each time a measurement occurs, coordinating the system's response faster than light could carry a signal. The quantum Zeno effect has practical applications in quantum computing. IBM, Google, and other companies developing quantum computers use variations of this effect to protect quantum information from decoherence. The ability to freeze quantum evolution through observation might seem to allow faster-than-light influence, but once again, no usable information can be transmitted this way. The universe maintains its speed limit even in the quantum realm. Now let's explore the holographic principle, one of the most profound ideas in modern physics. This principle suggests that all the information in a volume of space can be encoded on its boundary, like a hologram. The three-dimensional world we experience might be a projection of information stored on a two-dimensional surface at the edge of the universe. If true, this could mean that what we perceive as faster-than-light motion in 3 dimensions is actually perfectly normal motion in the underlying two-dimensional reality. Juan Meldesena's AD/CFT correspondence, proposed in 1997, provides mathematical evidence for the holographic principle. This duality shows that certain gravitational theories in higher dimensions are equivalent to quantum field theories in lower dimensions. Calculations that seem impossible in one framework become simple in the other. What appears as faster-than-light correlation in one description might be ordinary local interaction in the dual description. The holographic principle has been tested using quantum systems that simulate black holes. Researchers at MIT and Caltech have created tabletop experiments where quantum circuits mimic the behavior of black holes, including their holographic properties. These experiments suggest that information falling into a black hole isn't destroyed, but is encoded on the event horizon in a scrambled form. The scrambling process appears to happen at the fastest rate allowed by quantum mechanics, but still not faster than light. Let's venture into the realm of cosmic strings, hypothetical one-dimensional defects in space-time that might have formed during phase transitions in the early universe. These aren't strings in string theory, but topological defects like cracks in ice. If cosmic strings exist, they could be thinner than a proton, but stretch across the observable universe, containing energy densities that dwarf anything we can create on Earth. Cosmic strings would warp space-time around them in extraordinary ways. 2 cosmic strings moving past each other could create closed time-like curves, potentially allowing time travel. The space near a cosmic string would be so distorted that circumnavigating the string would require traveling less than 360 degrees. You could return to your starting point without making a complete circle. Light passing near a cosmic string would create multiple images of background objects, a phenomenon called gravitational lensing. The cosmic microwave background radiation, mapped by the Planck satellite and other observatories, shows no clear evidence of cosmic strings. However, pulsar timing arrays like NanoGrav are searching for gravitational waves that cosmic strings would produce as they vibrate and decay. If detected, cosmic strings would provide a window into physics at energy scales far beyond what any particle accelerator could achieve. Now consider negative energy and exotic matter. The Alcubierre warp drive and traversable wormholes both require negative energy density, regions where the energy is less than that of empty space. While this sounds impossible, quantum mechanics actually allows negative energy in certain restricted circumstances. The Casimir effect, where quantum fluctuations between 2 metal plates create negative energy density, proves that negative energy can exist. However, there seem to be strict limits on negative energy. The quantum inequalities, developed by physicists Larry Ford and Thomas Roman, show that the magnitude and duration of negative energy are severely constrained. You can have a region of negative energy, but it must be surrounded by positive energy that more than compensates. Any attempt to create enough negative energy for a warp drive or wormhole appears to be forbidden by these quantum laws. Stephen Hawking's area theorem, recently confirmed by gravitational wave observations, states that the total area of black hole event horizons can never decrease. This connects to the second law of thermodynamics and suggests a deep relationship between gravity, quantum mechanics, and information. When LIGO detected the merger of 2 black holes, scientists verified that the final black hole's horizon area exceeded the sum of the original 2, exactly as Hawking predicted 50 years earlier. This brings us to one of the most exciting frontiers in physics, emergent spacetime. What if space and time aren't fundamental, but emerge from something deeper? In this view, the speed of light limit might not be a fundamental law, but an emergent property of underlying quantum entanglement. The ER equals EPR conjecture, proposed by Meldesena and Susskind, suggests that quantum entanglement and wormholes might be the same phenomenon described in different languages. If spacetime is emergent, then what we perceive as faster-than-light limits might be analogous to the speed of sound in air. Sound can't travel faster than air molecules can transmit pressure waves, but this isn't a fundamental limit. It's a consequence of air's molecular structure. Similarly, light speed might be the maximum rate at which the underlying quantum structure of spacetime can transmit information. Loop quantum gravity, one of the leading theories attempting to unify general relativity with quantum mechanics, suggests that space itself is quantized at the Planck scale, about 10 to the negative 35 meters. At this scale, space would be a discrete network rather than a smooth continuum. Information could only propagate through this network at a finite rate, naturally explaining why nothing can travel faster than light. The James Webb Space Telescope is providing unprecedented views of the early universe, showing us galaxies that formed when the cosmos was just a few 100 million years old. These observations are testing our understanding of how quickly structures could form after the Big Bang. Some of the earliest galaxies appear surprisingly mature, suggesting that star and galaxy formation proceeded faster than our models predicted. While this doesn't violate the speed of light, it shows how much we still have to learn about cosmic evolution. Let me tell you about the black hole information paradox and its connection to the speed of light. When matter falls into a black hole, information about its quantum state seems to disappear, violating quantum mechanics' requirement that information be preserved. Hawking radiation, the theoretical emission from black holes, appears thermal and random, containing no information about what fell in. This paradox has driven decades of research into quantum gravity. Recent developments suggest that information might escape from black holes, but in a highly scrambled form that takes an enormous time to decode. The information would be encoded in subtle correlations in the Hawking radiation, emerging at the maximum rate allowed by quantum mechanics, but still respecting the speed of light limit. The black hole would act like the universe's ultimate encryption device, scrambling information so thoroughly that it appears random until you collect nearly all the radiation. The firewall paradox, proposed in 2012, suggests that the resolution might be even stranger. To preserve quantum mechanics, the event horizon might be surrounded by a wall of high-energy particles that destroys anything falling in. This would mean that the smooth event horizon predicted by general relativity doesn't exist. Instead, information would be violently scrambled at the horizon and radiated away, never truly entering the black hole. Now let's discuss tachyon condensation in string theory. While tachyons as faster-than-light particles probably don't exist, tachyonic fields play an important role in modern physics. A tachyonic field has imaginary mass, indicating instability rather than faster-than-light propagation. When such a field appears in a theory, it typically means the system will rapidly transition to a different, stable configuration. The decay of unstable d-branes in string theory involves tachyon condensation. This process, studied extensively by Ashok Sun and others, shows how apparently faster-than-light instabilities actually respect causality. The field doesn't propagate faster than light. Instead, it rolls down a potential energy hill, converting potential energy into other forms. This mechanism might have played a role in cosmic inflation, driving the rapid expansion without violating relativity. Consider the fascinating world of metamaterials, artificially structured materials that can bend electromagnetic waves in ways that natural materials cannot. Scientists have created metamaterials with negative refractive indices, causing light to bend backward. In these materials, phase velocity can exceed the speed of light in vacuum, while group velocity, which carries information, remains subluminal. Researchers at Duke University, Imperial College London, and other institutions have pushed these materials to extraordinary limits. Some metamaterial configurations create the illusion of faster-than-light motion. By carefully structuring the material, Scientists can make a pulse of light appear to exit the material before it finishes entering. This isn't time travel or faster-than-light communication. It's a carefully orchestrated reshaping of the light pulse. The peak emerges early, but no information actually travels faster than light. These experiments beautifully demonstrate the difference between various definitions of velocity in physics. The quest to understand the universe's speed limit has led to some of the most precise measurements in science. Atomic clocks can now measure time to better than 1 part in 10 to the 18th. That's like measuring the age of the universe to within a fraction of a second. These ultra-precise clocks are being used to test whether fundamental constants, including the speed of light, vary with location or time. The NIST F2 cesium fountain clock in Boulder, Colorado, and optical lattice clocks in laboratories worldwide are pushing the boundaries of measurement precision. GPS satellites provide an everyday test of relativity and the constancy of light speed. The satellites orbit at 14,000 kilometers per hour, fast enough that relativistic effects matter. Their clocks run faster than Earth-based clocks due to weaker gravity, but slower due to their orbital motion. Engineers must account for both effects to maintain GPS accuracy. Without these relativistic corrections, GPS positions would drift by about 10 kilometers per day. Every time your phone accurately locates you, it's confirming Einstein's theories. Let's explore sonoluminescence, the mysterious phenomenon where collapsing bubbles in water produce flashes of light. When sound waves cause tiny bubbles to collapse violently, they heat up to temperatures potentially exceeding those on the sun's surface and emit light. Some theories suggest that the bubble collapse happens so rapidly that the bubble wall exceeds the speed of light in water, contributing to the light emission through a kind of Cherenkov radiation. The exact mechanism remains controversial, showing how even familiar phenomena can harbor deep mysteries. The universe might harbor objects called gravastars, hypothetical alternatives to black holes where a phase transition at the event horizon creates a bubble of dark energy. Unlike black holes, gravastars would have no event horizon or singularity. Matter falling onto a gravistar would be converted to dark energy at the surface, potentially releasing information back into the universe without violating the speed of light. While purely theoretical, gravastars show how our understanding of extreme gravity remains incomplete. Quantum teleportation, despite its name, doesn't violate the speed of light. When scientists teleport a quantum state from one particle to another, they're not moving matter or energy faster than light. Instead, they're using pre-existing entanglement plus classical communication to recreate a quantum state at a distant location. The classical communication step, limited to light speed, is essential. Without it, no information transfers. Teams in China, Austria, and the United States have teleported quantum states over thousands of kilometers, but always respecting relativity's limits. The Unruh effect predicts that accelerating observers will perceive empty space as filled with warm radiation. An observer accelerating at 10 to the 21 meters per second squared would see empty space glowing at room temperature. While we can't achieve such accelerations directly, analogous effects have been observed in laboratory systems. This phenomenon suggests that the vacuum isn't empty, but seethes with potential particles that become real under extreme conditions. The Unruh effect respects the speed of light while showing that the concept of empty space depends on your motion. Recent observations of fast radio bursts have provided new tests of the speed of light's constancy. These mysterious millisecond pulses from distant galaxies travel billions of light years to reach us. By measuring how different frequencies arrive at slightly different times, an effect called dispersion caused by interstellar plasma, astronomers can test whether light of different energies travels at the same speed. The CHIME telescope in Canada and the Parkes Observatory in Australia have detected hundreds of these bursts, all confirming that light speed is constant to extraordinary precision. Let's consider the role of the speed of light in the anthropic principle. If light traveled much faster or slower, the universe would be dramatically different. Stars might burn too quickly or not at all. Chemistry might be impossible. The fact that light speed has just the right value to allow complexity, and life has led some physicists to propose that multiple universes exist with different fundamental constants. We observe this particular light speed because we couldn't exist in universes where it's substantially different. The speed of light also determines the size of atoms through the fine structure constant. If light speed were different, atoms might be unstable or unable to form molecules. The electromagnetic force would have different strength relative to other forces. The delicate balance that allows carbon-based life depends critically on light speed having its observed value. This cosmic fine-tuning remains one of physics' deepest mysteries. Research into quantum gravity suggests that space-time might become foamy at the Planck scale, with quantum fluctuations creating tiny wormholes and black holes that appear and disappear in 10 to the negative 43 seconds. This quantum foam might affect how light propagates over cosmic distances. The Fermi Gamma Ray Space Telescope has searched for such effects by timing gamma ray photons from distant cosmic explosions. So far, space appears smooth even at scales far smaller than we can directly probe. The observations from Fermi have placed stringent limits on quantum gravity theories. Photons of different energies from gamma ray bursts billions of light years away arrive within milliseconds of each other, showing that space remains smooth to at least 1 part in 10 to the 17 of the Planck scale. This incredible precision demonstrates that if space-time is quantized, the effects are far subtler than many theories predicted. Now let's delve into the concept of superluminal motion in astrophysical jets from active galactic nuclei. Beyond the quasars I mentioned earlier, we now observe thousands of these jets across the cosmos. The Very Long Baseline Array, spanning from Hawaii to the Virgin Islands, acts as a telescope the size of Earth, resolving details in these jets smaller than a light year across despite distances of billions of light years. Some jets show apparent speeds up to 40 times the speed of light, the most extreme superluminal motion ever recorded. The jet from Galaxy M87, which hosts the black hole first imaged by the Event Horizon Telescope, extends 5,000 light years from the galactic core. Different parts of this jet show varying degrees of superluminal motion, helping astronomers map the three-dimensional structure and orientation. The fastest-moving components are traveling at 99.9% light speed at angles of less than 20 degrees to our line of sight. The combination of extreme speed and geometric projection creates the illusion of faster-than-light motion. These observations have revealed that supermassive black holes can accelerate matter to speeds incredibly close to the ultimate cosmic limit. The magnetic fields near these black holes reach strengths of 10,000 Gauss, 20,000 times stronger than Earth's magnetic field. These fields, twisted by the black hole's rotation, create natural particle accelerators millions of times more powerful than the Large Hadron Collider. Yet even with all this energy, nothing actually exceeds light speed. Consider the peculiar case of quantum entanglement in biological systems. Recent research suggests that quantum entanglement might play a role in photosynthesis, bird navigation, and possibly even consciousness. In photosynthesis, energy appears to travel through protein complexes by simultaneously exploring all possible paths, arriving at its destination with near-perfect efficiency. This quantum coherence persists for surprisingly long times in warm, wet biological environments where it should quickly decohere. The European robin's ability to navigate using Earth's magnetic field might involve entangled electrons in certain proteins in their eyes. When light hits these proteins, it creates pairs of entangled electrons whose spin states are affected by magnetic fields. The bird might literally see magnetic fields through quantum entanglement. While this doesn't involve faster-than-light effects, it shows how quantum phenomena that seem to require instantaneous correlations operate in living systems. Let's examine plasma wake field acceleration, a phenomenon that might seem to violate light speed limits, but actually confirms them beautifully. When an intense laser pulse or particle bunch travels through plasma, it creates a wake like a boat moving through water. This wake consists of separated charges, electrons pushed away and ions left behind. The electric fields in this wake can exceed 100 gigavolts per meter, thousands of times stronger than conventional accelerators achieve. The Awake experiment at CERN and the Bella Center at Berkeley Lab have demonstrated that electrons can surf these plasma waves, gaining energy at unprecedented rates. Particles reach 99% light speed in just centimeters instead of kilometers. But here's the key. While the acceleration is extreme, the final speed still approaches but never exceeds light speed. No matter how strong the accelerating field, particles asymptotically approach c without ever reaching it. Now consider the implications of loop quantum cosmology for the Big Bang. Instead of a singularity where densities become infinite, loop quantum cosmology suggests a big bounce. The universe contracted to a minimum size before expanding again. During this bounce, which lasted about 10 to the negative 43 seconds, the effective speed of light might have been different due to quantum gravitational effects. This could explain some cosmological puzzles without invoking inflation. The Laser Interferometer Space Antenna, or LISA, scheduled for launch in the 2030s, will detect gravitational waves from merging supermassive black holes across the universe. These observations will test general relativity in the strong field regime, where space and time are violently distorted. If the speed of gravitational waves differs from light speed even slightly, LISA will detect it. Any deviation would revolutionize physics, but most physicists expect Einstein's theory to pass this test as it has all others. The Dark Energy Spectroscopic Instrument, or DESI, is creating the largest three-dimensional map of the universe ever made, measuring the positions and redshifts of 40 million galaxies. This map will reveal how the universe's expansion rate has changed over cosmic time with unprecedented precision. If the speed of light has varied over billions of years, or if dark energy is more complex than we think, DESI will find evidence. Early results suggest the expansion history matches our models, but surprises may await in the full dataset. Let me share a profound realization about the speed of light and causality. The finite speed of light doesn't just limit how fast information can travel, it defines the very structure of cause and effect in our universe. Events separated by space-like intervals, where light couldn't travel between them in the available time, cannot causally influence each other. This creates a causal structure to space-time, determining which events can affect others. This causal structure is preserved even in the presence of curved space-time around massive objects. While space near a black hole is dramatically warped, light cones, the regions of space-time that can be causally connected, maintain their essential properties. No matter how you bend or warp space-time with mass and energy, you cannot create causal loops or allow information to travel faster than light. General relativity has this protection built into its mathematical structure. The concept of light cones leads to one of the most beautiful ideas in physics, the block universe. In this view, past, present, and future all exist simultaneously in a four-dimensional space-time block. What we perceive as the flow of time is our consciousness tracking along a world line through this block. The speed of light determines the angle of light cones throughout the block, setting the boundaries of what can influence what. Your future light cone contains all events you could possibly influence. Your past light cone contains all events that could have influenced you. This block universe perspective radically changes how we think about faster-than-light travel. If you could travel faster than light, you wouldn't just be moving quickly through space. You'd be moving outside your light cone, potentially traveling into your own past. The geometry of space-time itself, not just some arbitrary rule, prevents this. It's as if the universe's architecture is designed to preserve causality and prevent paradoxes. Recent experiments with quantum computers have probed the boundaries between quantum mechanics and relativity in new ways. Google's Sycamore processor and IBM's quantum computers can create and manipulate entangled states across dozens of qubits. While these quantum correlations appear instantaneous, researchers have confirmed that no information travels faster than light even in these exotic quantum states. The quantum advantage these computers provide comes from parallel processing through superposition, not from faster-than-light communication. The phenomenon of relativistic beaming shows how motion near light speed can dramatically affect what we observe. When matter moves toward us at relativistic speeds, Its emission is concentrated into a narrow beam pointing in its direction of motion. This makes approaching objects appear much brighter than receding ones. The jets from black holes can appear hundreds of times brighter when pointing toward us than when pointing away. This effect helps explain why we see some active galactic nuclei as blazers. Their jets happen to point almost directly at Earth. Let's explore what happens at the edge of the observable universe. The cosmic horizon, about 46 billion light-years away, marks the boundary of what we can ever observe. Galaxies at this distance are receding from us at light speed due to cosmic expansion. Their light is redshifted to infinity. Photons from beyond the horizon will never reach us no matter how long we wait. This creates a fundamental limit to knowledge. There are parts of the universe we can never observe or influence, no matter what technology we develop. But here's something remarkable. The cosmic horizon is observer-dependent. Beings in a galaxy 10 billion light-years away have their own cosmic horizon, which includes regions we can't see and excludes regions we can observe. There's no universal edge to the observable universe. Every point in space has its own horizon. This relativity of horizons emerges directly from the finite speed of light combined with cosmic expansion. The study of primordial black holes has revealed another apparent faster-than-light phenomenon. During cosmic inflation, quantum fluctuations were stretched to macroscopic scales faster than light. Some of these fluctuations might have been dense enough to collapse into black holes immediately after inflation ended. These primordial black holes, if they exist, would carry information about physics at energy scales we could never achieve in particle accelerators. The LIGO and Virgo detectors are searching for gravitational waves from primordial black hole mergers. Consider the role of virtual particles in maintaining the speed of light limit. In quantum electrodynamics, the electromagnetic force is mediated by virtual photons. These virtual photons can temporarily have any speed, including faster than light, but they exist only as intermediate states in quantum calculations. Real, observable photons, the ones that carry energy and information, always travel at exactly c. The mathematics of quantum field theory naturally enforces this distinction. The vacuum birefringence predicted by quantum electrodynamics suggests that extremely strong magnetic fields can affect light propagation. In the presence of magnetic fields approaching the Schwinger limit, about 10 to the 18 Gauss, the vacuum itself becomes birefringent, splitting light into two polarization states that travel at slightly different speeds. While this effect has been indirectly observed near neutron stars, it doesn't violate relativity because both polarizations still travel at or below c. Now let's address a common misconception about the expanding universe. When we say distant galaxies are receding faster than light, we're not saying they're moving through space faster than light. Instead, space itself is expanding between us and them. It's a crucial distinction. No object moves through space faster than light, but space itself has no such speed limit on its expansion. This is why inflation could expand the universe by enormous factors without violating relativity. The integrated Sachs-Wolf effect provides evidence for dark energy's influence on cosmic structures. As cosmic microwave background photons travel through the universe, they gain energy falling into gravitational wells and lose energy climbing out. In a matter-dominated universe, these effects cancel. But with dark energy accelerating expansion, wells become shallower while photons are crossing them, leading to a net energy change. The effect has been detected by comparing CMB maps with galaxy surveys, confirming that expansion is accelerating without requiring any faster-than-light phenomena. Pulsar timing arrays like NA and OGRAV are searching for gravitational waves with wavelengths spanning light years. These waves, possibly from supermassive black hole binaries or cosmic strings, would cause subtle variations in pulsar timing. After decades of observation, NA and OGRAV has found evidence for a gravitational wave background, a cosmic hum of gravitational waves from across the universe. These waves traveled at light speed for billions of years before reaching us, carrying information about some of the universe's most violent events. The phenomenon of Bose-Einstein condensation creates states of matter where thousands or millions of atoms behave as a single quantum entity. In these condensates, created at temperatures billionths of a degree above absolute zero, the speed of light can be slowed to walking pace or even stopped entirely. Lena Howe at Harvard first slowed light to 17 meters per second in 1999, then later stopped it completely. But this doesn't violate relativity. It's the speed of light in the medium that changes, not the fundamental constant c. Recent experiments have pushed slow light even further. Researchers have stopped light for over a minute, storing its quantum state in atomic clouds. They've created negative group velocities where pulse peaks appear to exit a medium before entering. They've even stored images in atomic vapors and retrieved them later. These experiments demonstrate exquisite control over light propagation while always respecting relativity's fundamental limits. The search for Lorentz invariance violation, evidence that the laws of physics might depend on your absolute velocity, has reached extraordinary precision. Experiments using rotating optical cavities, comparisons of atomic clocks, and observations of high-energy cosmic rays have tested relativity to better than 1 part in 10 to the 19th. Every test confirms that physics works the same regardless of your velocity, supporting Einstein's postulate that led to the speed of light limit. The implications of these null results are profound. They tell us that if there is a preferred reference frame in the universe, a cosmic rest frame, against which all motion could be measured, its effects are hidden to extraordinary precision. The speed of light truly appears to be the same for all observers, just as Einstein proposed. This isn't just a quirk of light, it reflects the fundamental geometry of spacetime itself. Let's consider what we've learned from studying the most extreme environments in the universe. Near the surface of neutron stars, gravity is so strong that time dilation becomes extreme. Clocks on the surface run 30% slower than those far away. Light struggling to escape loses energy, becoming redshifted by factors of 2 or 3. Yet even in these conditions, where spacetime is warped almost to the breaking point, nothing exceeds light speed locally. The cosmic speed limit holds even when space and time themselves are distorted. The discovery of Kilonovae, the optical counterpart to neutron star mergers, has given us a new way to measure the universe's expansion rate. When LIGO detected gravitational waves from GW 170817, optical telescopes observed the resulting explosion. This provided both a distance measurement from the gravitational waves and a recession velocity from the light, allowing astronomers to calculate the Hubble constant independently. While there's still tension between different measurements, all confirm that cosmic expansion respects relativity's principles. Now, as we approach the culmination of our journey, let's address the elephant in the room: warp drives and science fiction's dreams of faster-than-light travel. Miguel Alcubierre's warp drive solution showed that general relativity doesn't absolutely forbid apparent faster-than-light travel. By contracting space ahead and expanding it behind, a spacecraft could surf a wave of warped spacetime. But the devil is in the details. You'd need exotic matter with negative energy density, and lots of it, potentially more than the mass energy of the entire observable universe. Recent work by Harold White and others has tried to reduce these requirements. By optimizing the warp bubble's shape and oscillating the field, the energy requirements might drop to merely planetary masses rather than stellar masses. But even these improved designs face seemingly insurmountable challenges. How do you create negative energy? How do you survive the intense tidal forces? How do you see where you're going when causality itself becomes problematic? Every solution creates new problems, suggesting that nature really doesn't want us traveling faster than light. The chronology protection conjecture proposed by Stephen Hawking suggests that the laws of physics will always prevent time travel and faster-than-light communication. Whenever a scenario seems to allow these phenomena, quantum effects or other physical processes intervene to prevent paradoxes. It's as if the universe has a built-in safety mechanism against causality violations. While we can't prove this conjecture, every investigation supports it. Consider what the speed of light limit means for our cosmic future. As dark energy accelerates cosmic expansion, galaxies will disappear beyond our horizon one by one. In about 100 billion years, All galaxies outside our local group will be beyond our cosmic horizon, invisible and unreachable. Future civilizations will see a universe containing only our merged galaxy, surrounded by darkness. They might never know about the Big Bang or cosmic expansion, because all evidence will have passed beyond the horizon. This cosmic isolation is a direct consequence of the finite speed of light combined with accelerating expansion. It means that if we want to explore other galaxies, we have a limited time, only the next few billion years, before they become forever unreachable. The speed of light limit doesn't just constrain our present, it shapes our entire cosmic future. But perhaps there's a deeper message in this cosmic speed limit. The fact that information can't travel faster than light means that the universe has locality. Events happen at specific places and times, and influences propagate through space at finite speed. This creates the possibility of structure, complexity, and ultimately life. In a universe without this limit, where everything could instantly affect everything else, the ordered cosmos we observe might be impossible. The speed of light connects space and time into space-time, creates the causal structure that allows for cause and effect, and sets the scale for all electromagnetic phenomena. It appears in the equation for mass-energy equivalence, determines the strength of electromagnetic forces, and governs how gravity propagates through space. Rather than being a frustrating limitation, the speed of light is the cornerstone upon which the entire edifice of physics rests. As we stand here in the 21st century, we've probed the speed of light limit with experiments Einstein could never have imagined. We've detected gravitational waves traveling at light speed across billions of light years. We've observed quantum entanglement that seems to transcend space while respecting causality. We've seen space itself expand faster than light, while matter within it remains bound by the cosmic speed limit. Every observation, every experiment, every theoretical development reinforces the same conclusion. The speed of light really is the ultimate speed limit in our universe. Yet this isn't the end of the story. Science is never complete. Perhaps future discoveries will reveal new aspects of this cosmic speed limit we haven't imagined. Maybe we'll find that the speed of light emerges from some deeper principle we haven't yet discovered. The universe has surprised us before and will undoubtedly surprise us again. What we can say with confidence is this: the speed of light limit isn't just a barrier to be overcome. It's a fundamental feature that makes our universe work the way it does. It enables causality, allows for the complexity we see around us, and connects every part of the cosmos through a web of light cones and causal relationships. We are all connected through this cosmic speed limit, bound by the same fundamental laws, part of the same magnificent universe. The next time you look up at the stars, remember that you're seeing them as they were years, centuries, or millennia ago, their light having traveled at the cosmic speed limit to reach your eyes. You're connected to those distant suns through beams of light that respect the same fundamental limit that governs everything from subatomic particles to galaxy clusters. We may be made of stardust, but we're also beings of light, living in a universe where information, matter, and energy all dance to the rhythm set by the speed of light. Thank you for joining me on this journey through space, time, and the fundamental limits of our cosmos. The universe may have a speed limit, but there's no limit to human curiosity and our quest to understand the magnificent cosmos we inhabit. Keep looking up, keep asking questions, and remember, even if we can't travel faster than light, our imagination and wonder can span the entire universe in an instant.